welcome to this presentation that will be focusing on collaborative aspects of model-based system engineering in what we call large system development. This is what we have applied in Galileo Second Generation, and we will see in a minute what this means. This presentation will reflect work we have been carried out in the last 5 years, more or less, and work which is foreseen ahead of us in the context of the Galileo program. So the outline of this presentation, we will give, first of all, some introduction to what the Galileo system is, in terms to explain how large it is and its complexity. And then the next part of the presentation will be the presentation of what we have been carried out so far in terms of collaborative work, before focusing on the work we foresee in terms of further collaboration and extending the collaboration among the different stakeholders which are part of the program. And we'll provide some concluding remarks, lessons learned out of what we have been doing. So first of all, introduction of the Galileo program and its complexity, what we call a large system. So Galileo is the European navigation system, which started in terms of definition in the 90s, and which is now in basically in full deployment for its first generation, with first satellites that was launched in 2005, and since 2016 providing service to the public. The core of the system is a constellation of satellites, which are currently 28 in orbit, and a ground segment which is deployed worldwide. So this is also quite something remarkable compared to other systems. And today we can count more than, I think, 4 billion users, which means Galileo is basically embedded in most of the chipsets which are coming on the market. And basically, if you have a smartphone quite recent, you have Galileo in it. The system, because it has been defined in the 90s, you can imagine that it has been evolving and it's not static. It has been already evolving since its early definition. And for the second generation, which is to be deployed, it's addressing a more significant set of evolution compared to the evolution which we have seen along the last years for the first generation. So basically, second generation, what we call second generation is a full deployment of space segment and ground segment of the system, of the new features. But as you can see here, it's a lot about improving, increasing. It's not really about including additional things in the system, but more in terms of improvement, which could turn out to be just having better algorithm or better using certain capabilities which are more or less already there. And since the deployment is progressive, the important thing is also that it will not come in one go, but it has to come on top of a system which is already deployed and working, without obviously interrupting service to the users. So this is a bit the programmatic envelope, and in terms of technical complexity, I'm not going into the details of this picture, but basically I mentioned earlier satellite constellation and a core ground segment which is deployed worldwide. So this is what you have here in the slides in the more or less purple box. But you have also many other boxes. And in particular, we have a set of service facilities, being Galileo Service Center or Search and Rescue Centers and so on. We have operational facilities to be able to carry out our launches or other things like this, also validation infrastructure. And all this is part of the ground infrastructure. So there's more than 15 other boxes besides the constellation and the ground segment. And on top of this, all this core infrastructure of the Galileo system is interfacing to more than 30 external entities, which could be, for example, timing laboratories in Europe, or the stakeholders such as ESA, ESA, and USPA. So all this is the core of the system. Many different stakeholders, subsystems, each of the box, you can see it as a subsystem, and interfaces. So it's basically what you have to take from this slide in terms of complexity. And just to add another layer, there is also the fact that in the Galileo program, we have a dimension of security. So actually for each of the system, each of the subsystem, rather, which is here, you may have also some different security levels to be addressed. So now we're moving on to what we have done in terms of collaboration so far for the development of or the definition of the Galileo Second Generation system. So starting with a bit of history, Galileo First Generation was not done per se using MBSE technologies, just for the simple reason it was not really existing. And when we started addressing second generation and starting to do full definition of the system design, it was clear to us that the system was extremely complex. And it would be difficult to keep it consistent along the way with the changes of requirements that we would be experiencing, and to be able to maintain consistency throughout the different subsystems. So we had to find a good methodology, and MBSE was starting to be much more on the table at that time. So in 2018, we decided to go for MBSE. And the first thing we had to do was actually to choose a tool. And from our industry, we received several proposals, and the one that was the most appealing to us, and maybe the more mature at the time as well, was Capella, with the Team for Capella environment, which was allowing us to do collaborative system engineering or co-design, because as I explained before, the system is very large, and therefore we need to have several system engineers working concurrently on the same model, basically. And the advantage is also that we could work remotely, because we were not all co-located in the same location. Then we were basically new to MBSE for all of us with already some experience, so we got some team training in order to get the same base in terms of model-based system engineering. And we had at the beginning a lot of brainstorming on how to approach the problem, because all the tools, I mean, it's true for Capella, it would have been true for others, they are quite rich, and we don't necessarily need all the features, and we need to define a common way of working together. So this has been a big part of what we have been doing, a big ramping up in terms of the team, and a lot of discussion to find a good way forward. So then we started with some developments, and of course, you don't succeed in the first go. We had a lot of redos, and also defining what you do in operational analysis or system analysis, logical analysis, the level of details, diagrams you would be using was not so easy as we were progressing. So we went to quite some level of details, starting from our system analysis. And when we had produced a first model for our system requirement review, it was clear that part of our system was also very detailed. It's also due to the fact that we have heritage from first generation system where we know how things are implemented. So doing analysis at more functional level is slightly more difficult. So the first model we produced, I mentioned that we have a security aspect in the program. We limited ourselves to work in our own classified environment, which is already quite wide, to do this first, the production of the first model. We decided at some point that it was too complex during the system requirement review. We had also a number of changes to accommodate. We had to introduce the security part. So all brought us to redo and to restart from scratch, because we could see that we would not be able to move forward. So basically, what I mean is that we went above a certain level of complexity. There was a limit, and the best way was not to try to tune and amend the model we had, but rather to start and taking our lessons learned from the first development we did to remain within a complexity limit which would be acceptable. So now I will approach more the security aspect, which we had also to address in a collaborative manner. What we have in Galileo is several security levels, which are a mix of classification levels and need to know. And at the end, it's one system. But of course, we have restriction in who has the right to access certain information. So it so happens that the number we have is 5 branches to compose our model, but it could be any other number. 1 branch is unclassified, and 4 of the branches are classified, but with different access rights. The security levels, as you are progressing, are more and more restrictive, so less and less people have access to them. And we could also aggregate them, of course, to have a full picture of the full system. And it works a bit like the Matryoshka with the in terms of access and relationship. So how did we do this? It's written already in the title of the slide. We are using diff merge. So the principle is that we have been developing a reference, which was the unclassified model, with as much as possible all the system functions and logical components that are needed in the system, because their content might be classified, but the name can be unclassified, so we could make them appear in the unclassified model. So once we had something solid enough in terms of unclassified model, we took it in our classified environment and we started developing each of the security branch in parallel, in order to have parallel work and not wait from the result of the first security level to start developing a second one. But of course, you cannot avoid that you need to make amendments to the unclassified model. So over time, at some point in time, we had a second version of the unclassified. And what we had to do is to get, again, all the security branches adapted to the new unclassified version of the model. So to do so, we are using the diff merge in a way which is a diff merge 3-way, where we get the original unclassified reference and the new unclassified reference together with the security branch. And these 3 branches are used to, are compared basically and merge to create the new security branch of the same level, the sec1 and the sec1-2 that is created. And we do exactly the same for the second and last version. And this allows us to have a new version of our system design, completely synchronized, to the same reference, and we could even concatenate it to have the full picture of the full system design. So what we learned by doing this in working collaboratively is that clearly we had to be very strict in terms of methodology. It was true in the unclassified environment in order to exchange information, because we had many engineers working together. But in the, with respect to the security, it's also very useful to facilitate the synchronization if you have the same way of developing, meaning the same views, the same type of explanations that you find back in the different branches of your model. We could also, and this is something also very important, try to put everything into the model, which means also the documentation of the information we have. We are not just using the diagrams, we are trying to describe them as much as possible, to describe the exchanges between the function, etc., to have really all the information inside the model. And then we used also some other artifacts that, like automatic coloring scheme. It can sound nothing, but it's very useful visually to know if you are addressing functions that belong to the space segment, the ground segment, a specific service facility, and so on. This color coding was also, it's something basic, but very useful. And then on the documentation, I was mentioning we try to put as many things as possible inside the model, which means we tried also ultimately to generate any document for the design definition and design justification files that we need to produce from the model directly. And this we did it with M2Doc. There's a bit of a pain in preparing the scripts, but then it allowed us to have very structured documentation for all the part of the system, and it helped us also kind of validating our model in terms of consistency and completeness, rather than looking in every single corner in Capella itself. So there were a lot of benefits in doing so, and trying to have an harmonized documentation, and also we don't need to write on the side complementary documents compared to what we have in the model. So moving on, we're going to look, give the floor to Alberto to look at more other aspects of collaboration with different stakeholders.
Yeah, thank you, Catherine. So on my part, I'll focus on 3 specific points that we have found very useful for collaboration. So Catherine has already mentioned that internal collaboration has been done mainly with Team for Capella. I'll focus more on how we do the collaboration with external stakeholders. So this is the architecture that Catherine has shown, and this shows a little bit how complex the Galileo system is. So in here, we can identify that we have many subsystems in the Galileo. So we can divide the Galileo into subsystems, segments, and other components. We also have several stakeholders. So those could be internal to ESA or external, like the European Commission or industry. We talk about the supply chain or the subcontractors of the prime, etc. So there are many stakeholders that we have to take into account when we do the architecture of a system, especially of a system as complex as Galileo Second Generation. Then we have the complexity added by the security levels. So again, as Catherine has said, there are different need-to-knows and levels of security that we have to respect, and we cannot have always the full visibility. So that's a constraint that is very important for us in Galileo. And this means that we need some mechanisms to maintain the consistency and coherency at any point in time, to make sure any development, even if they are in parallel, because maybe we are in different security zones, they have to be coherent or they have to be synchronized at a given pace. So now I'll focus on 3 solutions we've found to these needs. I'll start with the first one, which is the system to subsystem transition. So the main user need here is that from ESA, we are the design authority of the Galileo Second Generation. So we have our Capella model, which is, again, sometimes can be seen by everyone, some of the pieces, and some of the pieces cannot be seen by everyone. And then there are some parts of them that are be done by a supplier. So what we want to get is to be able to transmit that part of the model. So let's imagine that one subsystem or one segment or one component that would be done by a certain supplier. with the system to subsystem transition, we are able to select that part of the model and to transmit that to the supplier. Okay, and that would be their specification of their subsystem. So they can use that to develop their subsystems as specification, and they will look for the solution to what has been given by the customers, in this case ESA. And we can even go further, and we can ask the supplier to, if they would like to change something that's a proposed change or a request for deviation, they could do that by modifying that submodel, and then we can compare that with our full model and see where the impacts of that change would be. So in that sense, we can send them a partial model. They could modify that model, and we could try integrating that into our whole system model and see if we accept or reject that change. So that complete cycle is what we call system to subsystem and back. And that's something we've been successful in doing with the system to subsystem transition. Just going a bit on the details for those that are interested. This plugin allows for two types of transformations. The first one would be the vertical transformation, and the second one would be the horizontal. In this case, we are using the horizontal because the vertical one, what it does is transform from the logical level to the system level, so it makes a model transformation. So it's not really suitable for us when we want to send something to the supplier and then integrate it back with modifications into our whole system. So we've used the horizontal transition, which means that the suppliers can also do a vertical one if they are developing their subsystem with Capella, depending on their tool choice, if they are using MBSE or not. So that's the first of the points I wanted to talk about. The second is really the link between the system architecture and the requirements. So our system development uses several tools, and two of those are DOS for the requirements and Capella for the architecture. So in that sense, for us, it's very important to maintain the traceability and the consistency between both. And also that traceability has to be dynamic, meaning that something is changing in one, it has to be the impact has to be analyzed in the other. So in that sense, for this linking between the requirements and DOS and the functional and physical architecture in Capella, we have explored different solutions. One would be using the requirements viewpoint in the tool, but that would mean re-importing the requirements every time there is a change, or managing the requirements in Capella. One solution we are currently using is using Rectify, which is an additional tool and allows us to create these traceability links by importing the DOS modules and the Capella models into Rectify, and then making the traceability in there. So making just an image of that, and the links are stored in Rectify. And another solution we may be exploring in the future, it could be publication for Capella that would allow to link Capella with some PLMs tools where the requirements would be stored, and that would allow us to have everything in the same place and to make the traceability between both. So that's still something is not fully solved, but it's really important for us to maintain this traceability between the textual requirements and the architecture in Capella, so both are coherent and complete. And the third and last point is the communication of the models to external stakeholders. So inside the team, as we said, we mainly use Team for Capella, or we can use some kinds of exports, but we have also some external stakeholders that may include management or customers or other external entities, which they may be not trained to MBSE, they are not trained to the Arcadia methodology or the Capella tool. So that still remains an MBSE pain point for any methodology, any tool. And in our case, it's also something very, very important we have to take care of. So for here, we use a combination of several methods. The first one is we use a lot M2Doc to be able to export a model into a document. So we extract the diagrams, but we also extract tables and text from the model. So the model is given in a certain order, because one of the difficulties we find when using MBSE is that it's navigating the model. So stakeholders or the reviewers, they don't always know how to navigate the model. They may find it a little bit difficult, and it's not something we can train everyone to do it, because there are many occasional reviewers, let's say. So little by little, we think these situations will improve. But for now, we have to look for other solutions. One of them, as I said, this is exporting this into Word and PDF documents with M2Doc, which we have found quite useful. Another one would be using HTML exports. So this doesn't hide really the complexity of the model or of the Arcadia methodology, but at least allows opening the model without the Capella tool. So that has been useful for some stakeholders as well, and it's something we always provide for the reviewers. So those that are a little bit more familiar with Arcadia or with MBSE, they find it easier since they don't need the model for that. But well, there are some things that are not perfect, of course, that the semantic browser is not there, and people really have to be able to understand the methodology and the tool in order to do that. Other solutions we are exploring, or maybe exploring in the future. So Python for Capella, we haven't explored it yet, but we think it could be very interesting to use it to export in some other formats like Excel or others, just to query the model, identify what has to be extracted, and make an automatic export in other formats that M2Doc is not able to do. And again, the other one and the last one I will mention is publication for Capella, that would allow to have a website, let's say, internal, in which people just can come and see the model and even comment on that. Okay, so those are the 3 points I wanted to mention today about how to communicate with external stakeholders, meaning people not directly working on the model, so not the system engineers or system architects that are developing the model, that of course know it very well. And now Catherine will finish with some remarks on the presentation.
Thanks, Alberto. Indeed, I will give some concluding remarks, a bit in form of lessons learned from the work we have been doing and what we see from the new features that Alberto presented. So first of all, for us, collaboration was very important because of the extent of the system, the fact that we have several engineers working concurrently on the same system design in a very transversal way. And by using the Team for Capella version, let's say, of Capella, we managed to get to a model divided into several branches, but very consistent to each other, synchronized. A very consistent and coherent design by the different engineers. And in fact, we've been even growing the team, or we had some people changing along the way. And this has not been a big difficulty. They could jump into the model quite easily in the way we developed it. Another point is the fast generation of documentation. Once you have a script, you can run every day if you want the regeneration of the documents based on the model. And this can turn out to be very useful, and also to do the partial exports. When you believe one area of your system design is completed and you want to review it, let's say, calmly in one go, you can generate maybe the 20 or 30 pages rather than a full document out of what the different developments, even if several engineers were working together. Second aspect that we can draw as a conclusion is the very important, as when we work in a team, to have a common methodology. to get also eventually training, having a bit the same background on the tool, and to take sufficient time to reflect on this and to brainstorm and to have this common vision on how to make use of the tools, which are very rich. The native tool plus all the plugins eventually that are coming. Then for us, one tool very important is this diff merge capability embedded in Capella for performing synchronization. It turned out to work rather well. We have used it significantly, do a lot of synchronization along the way. Turns out to be good. Maybe the only remark at this point in time is to say that when it comes to the conflict resolution, when we do the diff merge, sometimes it's not very explicit, and we struggled a lot to understand a few of the messages. A lot of them are clear enough, but sometimes you wonder what the difference is and what the conflict could be. But ultimately, it works quite well. On the interaction between system and subsystems, work which has just been starting. As Alberto explained, we had first to choose the type of transition we wanted to make between system and subsystem, so we went for the horizontal transition. It works rather well. Now what we may figure out is that depending on the subsystem, you may want to pass some information or not to your subsystem designer. And today, the tooling we have might be a bit too light to do this kind of tailoring of the information we want to pass to the subsystem designer. So maybe it's an area where things have still to evolve to be more flexible, more agile, and adapted to any circumstance we have. Then to apply MBSE throughout the whole life cycle, we need to have mechanisms which are rather dynamic for traceability, and this is why actually requirement viewpoint is not very much adapted to the work we are doing. Also, when you have a long project life cycle, it means you have potentially different system version at different point in time. So you may have to follow different requirement baseline for these different point in times, and you need to have this agility to trace to each of the version. Reading, commenting the model is something we are looking for, and we expect that we could do things in the future with publication for Capella, because otherwise we are kind of obliged to go through the generation of documentation with M2Doc in order to have the model reviewed by people who are not familiar with MBSE. And even in Capella, it would not be easy. You would have to say, on this figure, I spotted this, or the text going with this exchange doesn't reflect such and such. We would expect that we have something much more interactive, hopefully with publication for Capella there. And this was a last conclusion I wanted to bring. Want to thank you for your attention. We expect there are questions coming. So Alberto and I have been presenting the work we have been doing so far. An additional contact point that we just bring here on the table as conclusion is also our colleague Eric Bouton in the Navigation Directorate. That is also following now the current work which is done on, for the Galileo Second Generation with Capella and Team for Capella.
Okay, I'm just gonna read the question. Can Capella be utilized to assess real change options for a system of such complexity?
Well, I think that for what's in the model, it's very, very appropriate for that. So the point I was saying that system to subsystem and then reintegrating the change, you can see the conflicts quite easily. There are some things can be improved, but I think for what Capella allows, it's very, very convenient. Then, of course, there are many details and requirements and other things that are not in Capella. So in that sense, Capella is not enough. But for whatever is in the model, we think it's a good option. Yeah.
Okay, next question. Do you use other tools along with Capella to write and manage requirements such as IBM doors? And how is the integration between those tools and the workflow adopted? So I guess you already partially answered this question. I don't know if you can complete it.
Indeed, the requirement baseline of Galileo is currently in DOS. Historically, it has always been there. And this is actually why Alberto was mentioning the usage of the rectify tool, which is a plugin which run on top. So basically, you take an image of Capella and you upload your DOS database into rectify so that you can establish links between the model and the requirement database. So you can link function to functional requirements. You can also link interfaces with your IRDs or ICDs, etc. And we expect the same from publication for Capella, which then would be used if we move actually from DOS to other tools. I think it would work with DOS next and Polarion at least, if I'm not mistaken. But then we would need to change the tool or the plugin on top of Capella.
Okay, how did you manage all the interfaces in Capella? And if so, how?
So in this case, what we do is interface identification in Capella. So that's one of the steps of our system engineering process of identifying the interfaces and the functional flows that go from one subsystem to another. But we don't have the full ICD, so the interface control document in Capella. We don't think maybe it's worth it or is really, it's not really worth it to put all that information in Capella. You could do that. It may increase a little bit the complexity of the model. So for that, we use other tools or additional documents for that.
Basically, we use functional exchange item, and then the data model. But there is a field or a category which is more labeled as interfaces in Capella, and this one we didn't use it. So interfaces are managed more through the exchanges and the description of those exchanges at different level in the Arcadia methodology.
Thank you. So maybe more on the collaboration. Have you worked with external engineering teams natively using SysXML like Magic Draw? And if so, how have you worked through incompatibilities between the Capella system models and SysXML modeling?
So not in the scope of Galileo so far, but okay, we also work in other projects. For example, provide support to other projects with other suppliers, and we use different tools. And we are working on some solutions for this. So actually, what we have identified is that the main problem of interoperability is not because of the tool or because of the format. Is really about the semantics. So Capella has some very specific semantics of what's a system function, logical function, physical component, logical component, etc. And depending to who you are talking, it doesn't really depend on the tool. It depends really on the company. Different companies, they have different methodologies, and they implement that methodology on top of SysXML. So they have something called function, something called interface, and really the mapping between those semantics of what's done in both parts is what really is problematic. So I don't think you can really do a mapping Capella to SysXML, because SysXML is, let's say, just a template that is done to be customized. So really is a mapping that you have to do per case by case for each project. Well, in the agency, we have several initiatives to solve that. regarding ontologies and MBSE hub, etc. But that would be the subject maybe of another presentation.
Okay, I have a couple of questions related to the effort. I'm going to display this one. Could you give us some information about the size and scope of your modeling effort? I mean, how many users, both internal and external to ESA, were involved with your model? Did you have any computational performance issue regarding the use of Capella? Have you had any experience in reporting bugs and feature requests, and how swift was the response?
So in terms of size of our team, so we were, I think, five, 6 person developing concurrently the system at any point in time. So it's not very large, but maybe at the end 10 people were knowledgeable about developing the model, but only 5 of them were actually involved in developing it concurrently. There might have been 2 persons from the same company, but basically we were working with a consortium. So myself on either side, and then several industries involved. So this meant that we didn't really experience limitation. We had kind of more tokens than people working on the model concurrently. In terms of performance of Capella, it has evolved along the way, depending on the version of Team for Capella we had. We experienced quite some instabilities at the beginning when we were with Team for Capella 1.3. It was better when we moved to 1.4. But still, at some point in time, we started having issues. Don't really know all the details. We're contacting OBEO on this, and there are a few things that were maybe a bit strange in the behaviors we had, but our model had grown a lot. There's a lot of backups which are scheduled also in Team for Capella environment to save all the models which are under development. So it might have created some issues. We moved recently to version 6.1. And it looks like it's much more stable. It allows us also to put the model in different directories, while before all the models were in the same directory on our virtual machine. So might also explain that we get also in terms of stability. What we try to do is really to put in the, let's say, collaborative environment only the models which are under development. The models which are finished or not to be modified, they are accessible by the people, but they are not placed by default in the shared environment, because otherwise we could have backups all along the way that could create issues because it uses a lot of memory. So it's maybe, but it's more in terms of installation and storage of the models. But I must say, since we have moved to 1.4.2, it was already good in terms of stability and not having too many issues. And then in terms of reporting problems, and it's part of contractual basis, so it's rather quick to have a first go at least on analysis of the problems we experience.
Yeah, just to complement that, yeah, those maybe were the internal users and people developing. So the system architects or system engineers were maybe 5 or 6, but then people reviewing the HTML and documents, probably tens or 100 people probably have to review.
Wow. Tens of people. I mean, that's the full engineering team. But when we, as we said during the presentation, when we went to reviews, to formal reviews, we went to the documentation part. So you select also the information you pass. It's not like full HTML where people can see all the details, and even the figures you would not export in your document would be seen. So,
Okay, thank you. Maybe the last question, we have just a couple of minutes. Why did you choose to use Capella compared to any other MBSE tool?
Well, 5 years ago, when we asked our industry who was bidding to propose some tool for MBSE, we had two proposals which was coming with Capella. It's true that Thales was part of this bid, and we had another one which was coming with another tool. I think one of the aspects was the collaboration capabilities that were kind of already strong or coming with a dedicated version of Capella, which was Team for Capella, which was appealing to us. It was the possibility to have easily some training along the way during the project development, because Thales was supporting this to us. And it was, and also this we should not forget, for example, compared to a solution which would be based on SysXML, it's maybe much easier to use in the first place, to learn after a few hours of training with Capella, to be able to start doing something by yourself. Doesn't mean after that it's not complex, but there was maybe initial ramping up, which was quicker than with some other tools, at least the ones which were proposed on the table to us, which had absolutely to provide collaborative capabilities for us. This was really important.
Okay, thank you very much, Catherine and Alberto, for an excellent presentation, excellent session.
Thanks to you.
Thank you.
Thank you, bye-bye.